What about rotational systems? So for instance, what if something is rotating and moving? Like a mass is wrapped around a pulley, and as a mass falls, the pulley turns. However, you could also have a system with just one element, where like a yo-yo, where it's falling and rotating at the same time, which is very similar to something rolling down a hill. Rather than being acted on by tension from the string, this wheel is acted on by friction, and so it is caused to turn as it falls, just like this is turning as it falls. And so energetically, it's very different than pulling on a string to rotate something, because the energy, for instance, the potential energy that this loses, doesn't just turn into rotational kinetic energy or linear kinetic energy. It's shared between the two. And likewise, this gains rotational energy as well as linear energy, and this one as well. So a crucial issue is what this radius is, where this is attached, where this is attached, or where this rolls. So it's worth noting the behavior of these systems depends crucially on where we connect the string or where this rolls, because energetically speaking, if we connect the string very close to the center, the system will gain rotational kinetic energy much faster than linear kinetic energy, because as this falls, this will spin faster. Or from speaking from torque, the further out we put the string or connect the force, the greater the torque on the body is going to be, and the faster it will accelerate. So as this mass falls, it's going to be very different if it's connected on the outside or very close to the center. The same with the yo-yo. You know that if you connect, a yo-yo falls much slower than if you wrap around the rim. And likewise, as we roll down a hill, if we're rolling on the rim of a large dumbbell, the acceleration is very different than if we're rolling on a very small hub. So if this is wrapped around the rim, for the same amount of fall, this turns less. Why? Because this rotates through some angle theta, and if it were attached here, there would be this much string that comes off, or if it's attached here, there would be this much string that comes off. And I use this as a little r as opposed to the big R of the wheel. And so how does a kinematic shake out? Well, the distance we go, like here, for instance, the distance I move is going to be equal to the radius times the rotation theta. So if this rotates through some angle theta, from here to here, this wheel will roll this far and then be located around here. And this would be my delta x, and that would be my delta theta, how far it turned. And likewise, the same for the length of string and the rotation of these two objects. Likewise, the speed is the rotation rate times the radius, and the acceleration is equal to the angular acceleration times that radius. And again, when I say that radius, it's the radius that connects the rotation to the linear motion, not the radius of the object itself. And so when we look at kinetics, we recognize that we have two kinetic energies, the linear and the rotation. And we have to include both. And how are they related? They're related by this radius. So for instance, dynamics, we can look at the forces acting on this and recognize that the tension is not equal to the force of gravity. Why? Because the sum of the forces equal mass times acceleration, and this is accelerating downward. So the tension is going to be less. And so how does torque come into play? The torque that's angularly accelerating this object is due to the tension in the string, is due to the force of friction on this wheel, is due to the tension in this string. And the torque is going to be related to this R. It's very important we know the angular momentum is not related to the radius times the linear momentum. And so we want to recognize that these two things are very different animals and are not related along the same lines as this. And so this really doesn't come into play when we analyze these systems. So for instance, if we want to take a look at one of these systems, let me take this one. We know that the potential energy changes to kinetic energy. And that is mg delta h, that this falls, is turned into 1/2 mv squared, because it's moving, plus 1/2 I omega squared. And so the problem is we have two unknowns. We don't know the velocity and we don't know omega. But we know they're related by these equations. So I could put this in terms of a rotation, or I could make this substitution that this is v divided by r, and I can substitute those in, and then by knowing delta h, I can solve for either the velocity or omega. And then I can use them to find each other. Be careful. Do these masses cancel? And they don't. This is the mass of the object falling. This is the mass of the object falling. This is the moment of inertia of the wheel, which has to do with the mass of the wheel and depends on your radius. And keep in mind, this is something like 1/2 mr squared. That's the moment of inertia of the wheel, but this r is the little r that this connects to. If we want to look at this through a lens of dynamics, what we do is we identify the forces. We have tension in the string, and that's pulling down on this wheel and angularly accelerating it. And the tension is also pulling up on the mass, which is reducing its acceleration downward. And then we have force of gravity. And again, we know these are not equal if we're accelerating. So the problem is we have two unknowns again. We don't know the tension and we don't know the acceleration or alpha. But we know these are related. And so what I could do is I could set this up. The vector sum of the forces about this guy is equal to mass times acceleration, right? And so I could, the accountant comes in and I could say this is my positive direction, and I'd say mg, little m naught g, minus the tension, is equal to mass times acceleration. Now, we can get another equation because we can say now tension is the only torque acting on this body. So the sum of the torques is equal to I times alpha. And that torque is equal to force times radius perpendicular, and that's going to be the tension times the radius, because these are perpendicular at this point. And so now I have three unknowns. I have alpha, I have acceleration, and I have tension. But alpha and acceleration are related. Acceleration is equal to alpha times r. So I can substitute this in, and I can solve these two equations and find alpha and tension. Or I could substitute in alpha here and find acceleration and tension. Either way, I can find all three unknowns. Okay, so I solved this one for you both in dynamics and kinematics. I'd like you to do these two systems.